Hello viewers and welcome to the second episode of the series on the history of electronic media. In the previous episode, we discussed how the telegraph was invented and how it changed the world. Now in telegraphy, the messages are passed through wires. So entire world was crisscrossed through with telegraphic wires. But that was soon to change at the fag end of the 19th century, and that's the story that we are going to tell in today's episode. When these telegraphic messages of joy and sorrow were crisscrossing, that was also the time when scientists were beginning to understand the nature of electricity. Okay, like different scientists in different countries were doing experiments with electricity, and every day they were discovering new phenomena. For example, the phenomena of electromagnetic induction was discovered by Faraday. Before that, the phenomena of that like charges repel each other, unlike charges attract each other, and how an electrostatic charge can be stored in parallel plate capacitors, those things were discovered. Okay, so then the Ampere's law, that if there are two parallel wires carrying current, they can attract or they can repel depending on the direction of the current. So all these things about the nature of electricity and how electricity and magnetism are interlinked with each other were being discovered in a very piecemeal kind of way by different scientists in different countries. Okay, but it was all happening in the second half of the 19th century. And then James Clerk Maxwell, he was also an Englishman, he consolidated all the disparate knowledge about electricity that was understood till then, and he consolidated all that into 4 equations which are famously known as the Maxwell's equations. Now, so therefore, he gave a theoretical foundation to the behavior of electricity, and from the theoretical foundation one can predict that in such circumstances the electric charge will behave in this way. Say for example, if there is a container, then charge will reside on the outside. So all these things which had been experimentally shown beforehand was now given a theoretical foundation. But another offshoot, another byproduct of the theoretical foundation was a constant which was there to necessary to equate two sides of the equation. That particular constant showed a way to a very important phenomenon, and that is that if supposing there is an accelerating charge or a fluctuating charge, it will bound to have generate a magnetic field also. And then this fluctuating electric field and magnetic field can feed off each other, and that entire thing can travel infinitely in distance, detach itself from the source and travel indefinitely into the distance. Okay. Now this travelled with the speed of this field, fluctuating electric and magnetic field, which complement each other, which travels in space. The speed of this is the constant in Maxwell's equation, and which happens to be the speed of light. So that means one can conclude that any accelerating charge or any fluctuating charge is capable of producing electromagnetic waves that travel with the speed of light through space. So that was a conclusion that came out from Maxwell's equation. It was a kind of theoretical prediction. Now it was left to Heinrich Hertz show it in the experiment in his laboratory about whether this actually happens or not. Now this is Hertz's setup, very humble, very simple setup in his laboratory. So we have two charged metallic balls charged, which are connected to again two small openings. So when the metallic balls are discharged, then there is a spark that flows across the openings here, and at a certain distance again two such openings are there which are not connected to any charged body, any battery or anything. But when there is a discharge through the gap in that main setup, then there is a sympathetic discharge that was seen in that ring, which was placed at a certain distance, but which was not connected to the main setup in any way. It was just kept in the vicinity. That means there is some kind of an energy transfer, and that energy transfer is not happening through wire, it is happening through space, Okay, and that is what this electromagnetic wave is. You know, electric and magnetic energy traveling through space, and its speed is the speed of light, which was shown using Maxwell's equation. So that was Hertz's discovery. It was a very important discovery because it actually showed the prediction of Maxwell's equation to be correct. Now we shift our story to our very own city, Kolkata. And from communication with wires, that is telegraphic wires, the mode of communication now shifts to wireless communication. And this is something that was initiated by a Bengali called Jagadish Chandra Bose. Now, when Maxwell wrote his equation, Jagadish Chandra Bose was 5 years old. But when he grew up, he happened to read a book called The Work of Hertz and Some of His Successors, written by a scientist called Oliver Lodge. So Bose was fascinated by Hertz's experiment, and he wanted to try out something similar in his own laboratory. He did not have any laboratory, but he was given a teaching job at the Presidency College. So, in a small room in the Presidency College, just beside the bathroom, he was given an assistant who was basically an electrician cum a carpenter kind of a person. So, with the help of his assistant, he set up his makeshift laboratory, and in that laboratory, he designed what is known as a coherer. Okay, he himself gave the name coherer, which was capable of generating these electromagnetic waves in a sustained way. So he generated these electromagnetic waves, and then he wanted to give a public demonstration of whatever he had developed so far. So he called the commissioner of the city, who was an Englishman, naturally, a very stout Englishman, called him to his home, because in Presidency College, in such a small room, he could not give any demonstration. He called him to his home, and then he gave a demonstration of these electromagnetic waves by ringing a bell and also firing a small gun in the next room. That means the waves travelled round the walls to the next room. They energized the system, or the circuit kept in the next room, and the bell also rang and the gun was triggered off. Okay, so that was the first demonstration, and the newspaper carried this news. It was quite a spectacular news. The newspaper carried the news, and it so happened that the newspaper travelled all the way to England, because though most of the newspapers were British newspapers, so the news travelled all the way to England, and Lord Raleigh invited Jagadish Chandra Bose to give a similar demonstration at the Royal Institute. So that was a big occasion for Jagadish Chandra Bose. He collected money to go to England, and he gave the demonstration there at the Royal Institute. Now, at the Royal Institute, there was a young person in the audience called Guglielmo Marconi, an Italian who had settled in England. Guglielmo Marconi, who saw Jagadish Bose's demonstration, he took ideas from there and he devised his own setup. Now, Bose has used his setup to generate microwave, or these electromagnetic waves, radio waves as we call them today, and study their property. Okay, he did not, making commercial use of these radio waves had not crossed his mind. But Marconi, that way, was more maybe pragmatic, you may say, and he patented his device. He patented in this famous patent number 7777, okay, and it's called tuned or syntonic telegraphy. So Marconi saw the telegraphic use of his device, that one could send telegraphic messages using these radio waves, but without the use of wires. Alright. So Marconi set up his company, and the first message that he sent was across the Atlantic. The year was 1901, and he transmitted this first wireless signal across Atlantic between Cornwall and Newfoundland, and the distance was 2,100 miles. Okay, and the message that he sent was SSS, coded in Morse code, and in Morse code S is 3 dots. Okay, that means pip 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 is one S, then again pip pip pip, then again pip pip pip. So pip 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 means short bursts of this radio signal, okay, or the signal of this electromagnetic wave. 3 short bursts would make 1 S. So he sent this message SSS, and then eventually Marconi was given a Nobel Prize in Physics in the year 1909 in recognition of their contribution to the development of wireless telegraphy. Jagadish Chandra Bose was deprived of this award. He was his country was colonized by the British, and for whatever reason Marconi actually stole the thunder, you may say, and the world recognizes Marconi as the inventor of radio waves. But it so happens that Jagadish Bose had given this lecture demonstration in England, where Marconi was an audience, and only after that he got some ideas and he developed his own device. Maybe he was working on it earlier, but he definitely got ideas from Jagadish Bose's demonstration which he gave in England at the Royal Academy. Anyway, be that as it may, now there is one difference between Marconi's device and Jagadish Bose's device, and that is in the wavelength of the waves produced by their instruments. Now, Jagadish Bose was mainly working with short waves, that means short wavelength radio waves, which do not go very far. Whereas Marconi has device could generate long wavelength radio waves, whose wavelengths were say half a meter long, 1 meter long, or even longer. Now, long wavelength radio waves travel farther, just as red color travels farther in the optical spectrum. Similarly, long wavelength radio waves travel farther. And because he had always intended to cross the Atlantic, his message should cross the Atlantic, so he gave all his concentration on developing his long wavelength radio waves. And then he started his own company, and Marconi's invention actually became a lifeline for the ships at sea. That is what we have to admit, and it is entirely goes to the credit of Marconi, because prior to that, when a ship was sailing at high sea, the ship would might get lose all contact with the shores, and then if the compass didn't work properly, or if the night sky was overcast and they couldn't find direction from the stars, then the ship might even be lost. But now there was a constant contact between the ship sailing at high sea and the shore through these radio waves, because every ship set up a small radio wave office on its deck, and of course there was the ground office there, and constantly there was a contact with the shores and the ship sailing at high sea. So there was no chance of any ship getting lost. Alright, so it became the lifeline for all the ships. So here there is a radio operator at Marconi's company, which was established in 1897. Okay, now you may say the Titanic sank in the year 1912, I think. So why did the Titanic sink? The tragedy is that the Titanic, being such a prestigious, such a big ship, definitely it had a radio office, and there were 2 radio operators from Marconi's company. And in fact, the 2 radio operators have been given the credit of those who actually survived and who could be saved, is thanks to the tireless effort of these 2 radio operators who were constantly at work in that radio office in that ship Titanic till it sank. But unfortunately, 35 distress calls were given out of which they reached the shores of Italy and other countries, but another ship which was sailing nearby in the same sea, there the radio officers were off duty, and so there was nobody to decode the message and receive the messages which were sent out everywhere, okay, in every direction. So that was the tragedy. After that, so after the Titanic sank, there was this new rule passed that the radio office on the ship will never be off duty. Round the clock, somebody or the other will be on duty. People will work in shifts, but somebody or the other will always be on duty at the radio office in the ships. Okay. So now, of course, a radio office from the ship is totally, it has become obsolete, because now ships can be tracked through the satellite system, through the GPS system. Okay. So therefore, no need of keeping this radio office on the deck of the ship. That's not required anymore. But anyway, So Marconi's company restricted to communicating with ships through telegraphic message. So his kind of communication was purely wireless telegraphy using Morse code, but instead of tapping the key, sending out short bursts of this radio signal. But then there was further development to use these radio waves to carry voice. Okay. So for that, further electronic development had to come. So this is a typical circuit that can actually modulate a radio wave to carry voice. Alright, and the kind of modulation that is generated here, as you see here, this is called amplitude modulation. That means if supposing this is the radio wave here of a certain frequency, and which is called the carrier wave, and the one below, the wave below, is the sound wave produced by a voice or produced by a musical instrument. When the two are superimposed, then the amplitude of the radio wave will get modulated according to the sound wave, according to the pattern of the sound wave. And that is called amplitude modulation, which is done using a device like this, amplitude modulator. So there is a certain electronic device. So that means now these radio waves can be used to carry the human voice, and by modulating it with modulating the carrier wave with the signal which is corresponding to the spoken word. Okay. Now another kind of modulation which is more modern, more recent, is frequency modulation, where the frequency of the carrier wave is modulated, it's made to vary in the same pattern as the vibrations of the spoken word, or the voice, or the musical instrument, or whatever it is. So frequency modulation is more recent, and it is called the inventor of frequency modulation is Edwin Armstrong. The Edwin Armstrong actually invented this frequency modulated waves, but before that this amplitude modulation became the common practice, and the radio waves started being used for sending out the signals. Okay. Now the radio waves come in various frequencies. Okay, starting from a few centimeters or a few millimeters to 1 meter, half a meter, 2 meters, and so on. Alright. Now it was an accidental discovery during the World War. Actually it was an accidental discovery that if the frequency of the carrier wave is short, okay, within a few centimeters or millimeters, then those carrier waves or those radio waves are bounced off the Earth's ionosphere. Okay, it was a completely accidental discovery. Alright. So how? Now supposing this is the transmitter. Alright. Now if the transmitter is, it's a transmission tower, now if the tower is giving out waves in all directions, then the maximum horizon for direct transmission is, say, here, when it is just touching the Earth's surface. But it so happened that even beyond this horizon, the signals were received. And then it was realized that the waves that are going up in the atmosphere, they are getting reflected by the ionosphere and they are coming back. Now when that interesting discovery was made, which was an totally accidental discovery, then short waves started being used for sending out signals to very, very far away places, even to the other end of the Earth. Okay, say 180 degrees, that's the other end of the Earth. They've started being used to send out the signals. Alright. So therefore, amplitude modulation we can have with medium waves, and we can also have with short waves. And eventually when radio stations were opened in different countries, then their external services or overseas services were carried out only through short waves, because it was only short waves that would travel, bounce off the Earth's ionosphere and travel to right to the other end of the Earth. Now the Earth's atmosphere is created by radiation. When the sun's radiation hits the molecules of the atmosphere, many of the molecules are ionized, and that is how the ionosphere is formed. So therefore the ionosphere, the strength and the depth of the ionosphere, that is very much dependent on the activity of the sun. Okay. In the years of the quiet sun, when the sun is not very active, the ionosphere will be thin, and when the sun becomes active, the ionosphere also will become more charged and more energized. Okay. So, it is therefore the carrying of the short waves was also became very much dependent on the activity of the sun and maybe some other weather conditions also. Alright. So, that is why nowadays of course satellites are used instead of depending on the Earth's ionosphere. Satellites are used to bounce off the signals to the other end of the Earth. But even in the pre-satellite era, it was the ionosphere that played the role of the reflector. So, these are some very interesting discoveries that were made in this radio communication. First this wireless telegraphy, then radio waves carrying voice, and how they can be made to carry really long distances. Now, that brings us to the one person's name I should mention at the end of this lecture, which is Reginald Fessenden, because he was the first person to send out amplitude modulated signals to the high C using his home setup, and it was the Christmas Eve of the year 1906. And in this year, on the 24th of December, he sent out a reading from the Holy Bible, then a singing of O Holy Night, and some violin recitals. He amplitude modulated all these voice signals and audio signals and sent out to the high C. And that created a lot of stir and lot of excitement in the sea, because that was completely unexpected, and that was the beginning of radio broadcast. So, I think the radio broadcast, how radio broadcasting developed in different countries, that we shall take up in the next episode. So, in this episode we saw how telegraphy, wired telegraphy shifted to wireless telegraphy, and this wireless telegraphy gave way to carrying of voice and speech in air using radio waves. Alright, but how that transformed into broadcasting, that we shall study in the next episode. Thank you very much.